Hey guys, welcome back to Genius Learning. Today I have a problem from classical mechanics, and we see here in this system that we have two pulleys, massless pulleys, so we'll assume they're massless to make the math easier. And we have this rope that attaches both of these masses, okay? And if you picture them both starting off at the same time in this position, and we just push this ball over and make it accelerate towards the left. Okay, so we give it a little push, and now the system is accelerating and moving in this direction. Okay, so first let's identify the position of this ball here, this mass. And so we know this is theta, and we have this length as r, so that's just from here to here. Okay, so this side here is going to be r sine theta, and this side over here is going to be r cosine theta, which stretches from this whole thing right here. Okay, so now let's see, we're going to need to draw some free body diagrams. Okay, so free body diagrams and free body diagram for both systems or both masses. Okay, so first we have this mass here, okay, represented by this dot, and it is experiencing tension from the rope, right, that doesn't allow it to separate from the rope. Right, so it's feeling tension up and always mg going down, mass times the gravity. And for this mass over here, okay, it's a little bit more involved. So let's draw a dotted line here to represent this dotted line, and we have the rope going like that. Okay, so theta is in here, r is like that, and this represents the mass right here. Okay, so this mass here is experiencing a couple of things. Okay, so first it's experiencing the tension of the rope, right? Then we also have, like always, mass times gravity going down. Okay, and from that line we can extend this going downward, right? And we have a theta here, which is the same angle as this one. And now we can do adjacent over hypotenuse, right? Because if we do a triangle here, this is 90 degrees, okay? And this is gonna be the adjacent, this is gonna be the hypotenuse. So we have mg cosine theta, and opposite over hypotenuse, this is gonna be mg sine theta. Okay, but this one here, we're gonna write over here. Okay, so we're just gonna move this vector, or this side here onto this side over here, and we're gonna put mg sine theta. Okay, and this is the restoring force, because if this was just a pendulum, okay, as soon as the mass is moving this way, it wants to go in this direction in order to go back, and then once it passes the equilibrium point, it wants to go back into the other direction. And so we call that the restoring force. Okay, and so if we take a look at both of these free body diagrams as one, make it a little bit easier to understand it. Okay, this is this mass here, and this mass is over here. Okay, and let's see, we got, this is the rope connecting both of them. Okay, and so this one here is just experiencing mg, right, mass times gravity as it goes down, and this one here is experiencing mg cosine in the opposite direction. Okay, so it is being pulled by tension going up and mg cosine in this direction, okay, which is opposite to what this one is feeling, as it feels the tension going up and mass gravity going down, which represents this line. And so the acceleration, right, is in this direction. Okay. So let's use Newton's second law to solve this problem without Lagrangians. Okay, we're gonna try to solve this problem with torque and see what the difference is between Lagrangian and this other method that we can use. So we're gonna do the sum of forces, okay, for this system here. And we can see that the net force from both of these, okay, so the force that we're experiencing from this mass and this mass is going to be our net force, and that's going to be mg in the positive, right? We'll assign one direction positive, the other direction negative. So one direction here, I'll assign positive, and in that direction is the negative. Okay, so that's something that you have to establish when you're working these problems. What direction for you want to be positive or negative. Okay, so I want my positive to go that way and my negative to go that way. So that way my mg is the positive direction, okay? And let's see, so our force net is gonna be mg in the positive minus this tugging force over here that we feel as a result of this one being pulled in the opposite direction, okay? So force is equal to ma, so this is the formula here. Okay, so this is going to equal ma, mass times acceleration, and we're just going to rewrite this again, okay? And now this is a little tricky part. Our force net represents the total force of this system, and here we only have one mass. So they're both the same mass, but we have two of them. So we're gonna write 2m in place of the mass. So we have two m's, not one. Okay, and this side is a single m because that represents that one. And this side here is a single m because it represents this one. So the only reason we put 2m on this side is because it's the force net. It represents all the forces put together, and so it has to represent all the masses put together, not just one single mass, okay? So let's cancel out mass. We're left with a 2 here, and we can solve for acceleration. Okay, we divide by 2, and we're gonna have, so we take out the g's, and we have 1 minus cosine theta, and divided by 2, okay, we're good. So this is the acceleration that the system is going in. So we can calculate that using Newton's second law, right, the sum of forces. And so we're gonna leave that right there, and then we're gonna get the equations of motion using torque. Okay, so this is the acceleration of the system, and now let's try to find torque. Okay, so first we need the moment of inertia. Okay, the moment of inertia for these masses here is going to be I equal to mr squared. Okay, and we're going to need that in our equations of torque. So for torque, we have two equations. Okay, we're going to use tau, right, which is a vector, equal to r vector crossed with f. So that's 1. And the other one is tau equal to moment of inertia times, this is angular acceleration. Okay? All right, so these two formulas here, we're gonna need to fill in and then make them equal to each other. Okay, so let's look at the first one. And we're just gonna be looking for the magnitude, and so we don't need to worry about the vectors or in the direction that they're going. So just as a side note here, r hat, theta hat, and phi hat is spherical coordinates, which is what we're gonna be working in. And so, you know, r cross theta is gonna be phi hat, or r crossed phi hat is gonna be negative theta. Okay, so if you go in this direction, it's positive. Right? If you have theta hat crossed with phi hat, you're gonna get a positive r hat. Okay, but if you had theta hat crossed with r hat, you're gonna get a negative phi hat. And so if we go in this direction, it's negative. Okay, so we're not gonna need to use this because all we want is the magnitude, but for future problems, these vectors here correspond to this cyclic system over here. Okay, so let's deal with this right now. So we got tau is equal to r, which is the length, the radial length here, because we're assuming spherical coordinates here, and it's crossed with the force of the system. So the force of this system right here, okay, is going to be negative because going upward while it's swinging, it's being pulled downward, and we're going to identify that as negative mg sine theta. Okay, it's called the restoring force. So this is the restoring force, and that's always negative. Okay, so the restoring force down, negative. So we're gonna have tau is equal to negative mrg sine theta, and this here represents the magnitude of our torque. Okay, so we got that. Now let's find the second one. Okay, so for the second one, we're gonna use the moment of inertia, which is mr squared, okay? And the acceleration, we're just gonna keep as alpha, okay? Because we just want the magnitude again. So we got this, and we're done with both of those. Now let's set them equal to each other. Okay, so now we're gonna set tau equal to tau, okay? And so I'm gonna have I alpha equal to the other side here, which is r crossed f. And what did we get for I alpha? We got mr squared alpha equal to the magnitude over here, which is negative mr g sine theta. Okay, we can cancel out the m's, and it looks like we're gonna divide by r squared, and we're gonna leave an r on the bottom. So minus g over r sine theta, and that's it for this part. Okay, so if we use small angle approximation, all right, we see that sine theta could be approximated to theta, right? That means that this theta, even though it's drawn here, is a little bit larger than a small angle would be. we can just say that the angle is going to be around here. So, you know, small angle approximation, and it allows us to change this. Okay, so let's change this to negative g r sine theta. Oh, sorry, to theta. Okay, so let's write that again. So alpha negative g over r theta. Okay, we have this, but we need to simplify what this means. Okay, so when we talk about angular acceleration or angular velocity, okay, we're looking at theta, and when we take the derivative of theta, so theta is just the angular, you know, the angle that we're moving at, and if we want to know the velocity of how fast we're moving, then we need to take the derivative of theta. And so the derivative of theta with respect to t is theta dot, or we can write that as omega, which is the angular frequency, angular velocity, sorry. So this right here is the angular velocity, okay? And now if we take the derivative of omega, then we're gonna get alpha, which represents our angular acceleration. Okay, so if we just have theta, that's the angle that represents, you know, the displacement in the theta hat direction. If we take the derivative of theta, then we're looking at the angular velocity. So how fast did this move to the right is what this means. And if we want to know, is there a change in velocity, meaning is there an angular acceleration to that movement, then we take the derivative of omega, which is represented by alpha. Okay, so alpha is d omega dt. Okay, so if we look over here to theta dot, okay, that represents omega. We just took the derivative of omega. Okay, so if we take the derivative of theta dot with respect to t, which is the same exact thing, so is the same exact thing as taking the derivative of omega. Okay, so we have omega and we're taking the derivative of it with respect to t. That's giving us alpha. Now if we take the derivative of theta dot, which is the same thing as omega, okay, then we're gonna get theta double dot. Okay, so this theta double dot is the same thing as alpha, is the same thing as the derivative of omega. Okay, see if that makes sense to you. If not, rewind and try to understand this piece. But this notation here is the same thing as alpha, is the same thing as taking the derivative of omega with respect to t. Okay, it's the same thing as taking the derivative of theta dot with respect to t. Okay, so we're going to use this notation here and replace it with alpha, okay, because this is equal to alpha. So now we're going to have theta double dot, which is this one here, equal to negative g over r theta. Okay, now we got everything in terms of theta, which is our goal. And when we pass this to the other side, okay, we're gonna have theta double dot plus g over r theta equal to 0. And now we got something more familiar. So we should know what this differential equation solves to. And we know that the value, the constant in front of the theta is omega squared. And so omega squared is equal to G over R, and omega is equal to the square root of G over R. So this omega is the angular frequency. So angular frequency. That's different from the angular velocity. Okay, so make sure you don't confuse the two. So the angular velocity is just how fast we're moving in the theta hat direction, and the angular frequency will tell you the frequency in which we're making those rotations. Okay, so here is the equation of motion, and here we have the angular frequency. All right, and that's without using the Lagrangian. So there's a couple ways to solve this problem, but to find the equations of motion, we can either use torque or the Lagrangian, which we'll save for another video. Okay.